Okay, so from our last class, we were working on this example. We didn't finish it. Where from section 5.10, we're asking if this improper integral converges or diverges. Converges means that the improper integral has a finite answer. So remember, what is this? This is the area between the curve x times e to the x power and the x-axis from the limits negative infinity to 0. But what makes the integral improper is that you have a bottom limit of negative infinity. Okay, and so that is a type 1 improper integral. So the question was, if we draw, like we drew a picture. Hold on here. Okay, we drew a picture of the function x times e to the x, and from 0 to negative infinity, the entire function is below the x-axis, and we're wondering if the area, okay, this is a definite integral, even though it's an improper integral, it's a definite integral, so it represents the area between the function and the x-axis, and the question is the area finite? So it could potentially be infinite, because the left limit never ends, right? The left limit is negative infinity, and so as you graph the curve out to negative infinity, there's always an accumulation of area, a little bit more, a little bit more, a little bit more. The question is, will that add up to infinity? Okay, and it really depends on the rate at which the area is accumulating. So what we did is we said, okay, well, the techniques we learned in chapter 5 for integration dealt with proper definite integrals, where you had finite bottom and top limits. So what we're going to do is we're going to write this improper integral as the limit as t approaches negative infinity of a proper integral, Okay, so see, the bottom limit is t, and t we treat like it's finite. And then we're going to integrate this integral, the integral from t to 0 of x times e to the x dx. But then when our answer is going to be a function of t. And so what we do then is we take the limit as t approaches negative infinity, and that will get us our answer for our improper integral here. Okay, that's how you deal with these problems. Okay, and so we knew that we had to use integration by parts, and when we did integration by parts, we let u equals x and dv equals e to the x dx. Okay, that's what we did, and we did the integration just like we would do a section 5.6 problem. And we got down to here. This is where we finished. So our improper integral I is equal to the limit as t approaches negative infinity of negative t times e to the t minus e to the 0 minus the quantity e to the 0 minus e to the t. So the question is, what do these values go to? Okay, what do these functions of t go to? I mean, e to the 0, there's no question. I mean, that just equals what? That equals 1. So that's not affected by the limit. But what would e to the t go to as t goes to negative infinity? What does e to the t approach? What number? If you have e to the negative, that's right, Tina. E to the negative infinity is like, it's like 1 over e to the positive infinity. So e to the positive infinity is infinity, and so this is going to approach 0. The remaining issue is this term here, t times e to the t. Okay, you have t going to negative infinity, and then you have e to the t going to 0 as t goes to negative infinity. So when you have negative infinity times 0, is that a determinate form or an indeterminate form? Negative infinity times 0. That's indeterminate. That's right, Rodrigo. So how do we handle that situation then? How do we handle limits that where we have indeterminate forms? What special rule do we have to use? Do you remember? That's right, Tina. L'Hopital's rule. L'Hopital's rule. So let's continue the problem. So we're going to have to use L'Hopital's rule to find out what that limit's going to be. But at least we have the skill set to move forward with the problem. And this is why you needed to learn L'Hopital's rule. So we'll go to the next page. And we're going to apply L'Hopital's rule as you see here. Let me give you a moment to copy that down. Okay, question. Let's see. Notnell says, how come we didn't include the negative for t? That's a good question, Notnell. We are going to bring that back in. We are going to bring that back in. And you can see here that t times e to the t. That I mean, I'm not worried about the negative now. I'm going to bring that back in. But t times e to the t. Remember, that was the indeterminate form, negative infinity times 0. I write that as t over e to the negative t. So this now acts like negative infinity over infinity, which is indeterminate. I mean, okay, there's a negative there, but it's still indeterminate. Okay. So you take the limit. Well, you have your function f. You have your function g. And L'Hopital's rule says the limit as t approaches the negative infinity of f over g of this indeterminate form would be the same as the limit as t approaches negative infinity of f prime over g prime. Okay. And so that's going to equal 0. And now you see here, not now, I brought the negative back. Let's see, Tina has a question. Excellent. How come e to the t in the numerator became e to the negative t in the denominator? So, what you're doing is, hold on here. I mean, okay, let me put in a little step here. So t times e to the t is over 1, right? And so you're going to multiply by e to the negative t top and bottom. And so, Tina, e to the t times e to the negative t. Okay, this, let me see here. Maybe I can try to, hold on. That didn't work. Hold on, give me. So e to the t times e to the negative t is e to the 0. Because you got e to the t plus negative t. You add the exponents. And that gives you e to the 0, which is 1. So you get 1 times t in the numerator, which is t, and then 1 times e to the negative t in the denominator here. And that gets you e to the negative t. Tina, is that all right? Okay, good, good. All right, so now we are ready to compute the entire limit. So you had the limit, if we go back here, okay, if we go back here, you had the limit of, I mean, this is t negative t times e to the t minus 1 plus e to the t. I'm distributing the minus through there. And so you got the limit of the sum of 3 functions. That's going to be the sum of the limits of each function. And that's assuming the limits exist, but they do. And so that's how we get to this step here. And it turns out that we get a negative 1. We do get a negative 1 for our area. We knew the area would be negative, but we didn't know if it would be infinite or not, negative infinity or not. And it's finite. So our integral converges. Well, let's see. No, Tina. I mean, I have, let me see here. I mean, on the bottom, oh, okay, I see what you're saying. So, hold on here. For the L'Hopital's rule, when you were looking at the denominator here, negative e to the negative t, just don't worry about the negative. E to the negative t is going to be like, as t goes to negative infinity, it's going to be like e to the negative infinity, which is e to the infinity, which is infinity. So it's like 1 over negative infinity. Okay, that equals 0. All right. The negative's not the problem. The negative's not the issue in front. It's how the functions behave. Okay, good question. Good question. All right. Are there any other good questions before we move to our next example? All right, then let's move to the next example if we're good. Oh, I'm sorry. I guess I'll let you write this too. This is like a summary. It's a summary. So therefore, our area is equal to -1. See, the area, because the one limit goes to negative infinity, there's always a little bit more and a little bit more area being accumulated, but it doesn't accumulate fast enough to make it like an infinite area. And so the integral converges. It converges because the limit exists. When we talk about convergence, we're always talking in terms of limits. You're going to see that, for instance, when you learn about sequences. Sequences in chapter 8. Sequences can converge or diverge. And that's because you're taking the limit of the sequence. But that's chapter 8. All right, let me give you a moment to copy this down before we move on. Okay, so all right. Well, why don't let's move on then to the next example. If everybody's good, we'll move on. Okay. Here is another improper integral. I'll give you a moment to copy it down. All right, so Tyreek's question is the one I was hoping you'd be thinking about. This integral is improper, but you notice the limits are finite. 2 and 5 are finite limits. and yet we're calling it an improper integral. Now this is an improper integral of type 2. This is a type 2 improper integral, but why is it improper? What's the problem? What's the problem here? That's right, Esther. Very good. The 2, when x equals 2, okay, when x equals 2, what's 1 over the square root of 2 minus 2? That's 1 over the square root of 0. That's right, Cologne. And so you're getting an infinite, the function, if you were to graph it, what would the function do at x equals 2? What would you see in the graph? Because we know the function, well, I wouldn't call it a hole exactly, Cologne, but a problem for sure. When functions go to infinity or negative infinity, what do we see on the graphs? Think of like the tangent function, or that's right, Rodrigo, an asymptote. So this function has an asymptote. And if we look at the graph here, this is the function f of x equals the square root of 1 over x minus 2. Okay, this is the graph of the function. It ends at 5, but when x equals 2, at that value, there's an asymptote. And the question is the area finite? Because you know, you have an asymptote and you have, I mean, we're looking for an area. But you have this accumulation of area here that's building up. Right? The graph goes to infinity, so you're always getting a little bit more area, a little bit more area, a little bit more area. The question is the area finite or infinite? So this is called a type 2 improper integral, a type 2. And just like with the other improper integral, we have to, when we evaluate the integral, we have to have defined limits where there are no asymptotes. So I'm going to replace the 2 with a t. I'm going to replace that. And t is not going to equal 2. Right? T would technically be, you know, well, t is not, say, equal to 2. So now I'm going to integrate the integral from t to 5 of 1 over the square root of x minus 2 dx. I'm going to get an answer, but then I'm going to take the limit as t approaches 2. And of course, it's from the right because, you know, we're approaching t equals 2 from the right here. Okay, are there any questions up to this step? All right, well, how would we integrate this? What technique would we use to find the antiderivative? Substitution, absolutely. That's right. That's right. So what would we let u equal to, Rodrigo? What would u equal to? What would u be equal to? X minus 2, okay. So I'm going to let u equals x minus 2, du equals dx. And then we have here then, the integral I is equal to the limit as t approaches 2 from the right of the square root of 1 over u du, but the limits go from 3 and t minus 2. So the 3 limit comes from 5 minus 2, right? And the bottom u limit is t minus 2 because x is when x is t, u is going to be t minus 2 because u equals x minus 2. Now notice we have not taken the limit yet. So I keep my limit there. I don't work this problem without having my limit there. Okay. The limit should be there, right? All right. So this is just sort of standard integration. Of course, 1 over the square root of u, I'll write as u to the negative half. I like to do that because then I can do the, I can use the opposite of the power rule. Okay. All right. Are there any questions before we move on to the next page? Okay, Not-Nell's good. Thank you, Not-Nell. All right. Well, the antiderivative of u to the negative 3/2, of course. Oh, Sine? Yes, Sine. Okay. Sine's good. All right.
Hello, you said my name?
Yeah, I'm here. Do you have a question, Sine?
No, I don't have a question. Did it say I had a question?
Well, I thought maybe you had a question.
Oh, I'm sorry.
Because no, that's okay. That's all right. No problem. No problem. Okay, moving on. Okay, so my integral I now equals the limit as t approaches 2 from the right of 2 times u to the half power at 3 and t minus 2. Now, sometimes what students like to do, and I sort of find it odd, really, but sometimes what students like to do is they like to then, now that they have their antiderivative, they like to go back and replace the u with x minus 2. So you'd have the square root of x minus 2. And then they like to use the original limits of 5 and 2. And I even see this, I think sometimes in the help videos. I've seen like examples where that's been done. In other words, you could, now that you have the antiderivative, you could replace the u with the square root of x minus 2, and then replace the u limits with the x limits, which were originally 5 and t, and take the limit as t approaches 2 from the right. And if you do that, you will get 2 times the square root of 3. And it's okay. It's okay to do that. It's okay to do that. But my thinking is, why do that? Why not just work with your u limits that you have here? Why not, why make it to make an extra step for yourself? Just work with the u limits, put them in for u, and take the limit as t approaches 2 from the right. So I mean, well, I have a what the 2 times the square root of t minus 2 would be 2 times square root of 2 minus 2, right? And that, of course, is the square root of 0. So I'm just adding a few more steps here. That's 2 times the square root of 3 minus 2 times the square root of 0. And that's just going to be 2 root 3. So the integral converged. The integral converged. And actually, that's stated right here. The area is finite, and of course it's positive area because all that area was above the x-axis. Okay, all right, let me give you a chance to copy that. Let me know if you have any questions. Kahindi, what Kahindi's saying is t, technically, well, remember, Kahindi's asking why did you plug 2 in? Because we're not allowing t to actually equal 2, because then the integrand in the problem, the 1 over the square root of x minus 2, would be undefined at x equals 2. That's true, but remember what we're doing here is we're taking a limit. And since the limit exists, it's okay to put the 2 in there. It's okay. I mean, it's like, okay, put in 1.9999999, but that's how this is legitimate for computing the limit. It's the limit. So pretend that you didn't start out from that integral and you were just trying to compute this limit. Think back to calculus 1. How many remember when you compute the limit, if the limit exists, eventually you put in the value of like 2 in this case, or it's the same principle. Very good question. Let's see. Does this? Let's see. Notnell's question is. So if the integral was improper, it's an improper integral because there are 2 kinds of improper integrals, type 1 and type 2. This was a type 2 improper integral because the integrand function, the 1 over the square root of x minus 2, has an asymptote at x equals 2. Okay, and that means area could be potentially infinite. But this integral converged, so the area is finite, but it's still an improper integral. It's still an improper integral. It just converges. That's all. It has finite area. The area is finite. So the integral converges. All right, Notnell, comfortable with that? Okay, good. Okay, well then let's move on to the next one. We're going to try to do a variety here today. Okay. Wow, look at this integral. How many feel that definitely looks improper? All right, take a moment to copy it down. Okay, so in this problem here, we have, well, is it a type 1 or a type 2 improper integral? What would you say? That's right. That's right, Tina. Definitely a type 1. And this one is a little more interesting because you have infinity and a negative infinity. Okay, so what we have to do is we have to make the problem manageable for us. So we're going to split this integral up into two integrals. Okay, we're going to split it up into two integrals as you see. The first integral will go from negative infinity to 0. The second integral will go from 0 to infinity. And if we add those two integrals together, that's going to give us the integral we're interested in, the integral from negative infinity to infinity. But that's how you handle this kind of situation. And incidentally, the constants, the 3's, I'm going to pull out front. So my integral becomes 3 times the first integral plus 3 times the second integral. All right, let me give you a chance to copy that. Okay, is everybody comfortable up to this step here? All right, well, now what we have to do is we have to compute the improper integral I sub 1 and see if that integral converges. If that integral converges, then we're going to go and compute the improper integral I sub 2. However, if our improper integral I sub 1 diverges, then we're not going to bother computing the second improper integral. Okay, because if one of those improper integrals diverges, we're going to have a divergent improper integral. Okay, and so we proceed here. All right, here's the first improper integral. And I'm going to write the improper integral as the limit as t approaches negative infinity of the integral from t to 0 of x times e to the negative x squared dx. All right, and what are we going to use to handle this integral? What are we going to do to integrate this? Substitution. Okay, well, what substitution do we use? What are we going to let u equal to? Yeah. Well, Felicity, I would let u equal, you could let u equal negative x squared. I would personally let u equal x squared. But, you know, you could let u equals negative x squared, sure. And if you do that, okay, you're going to get a new improper integral. Okay, are there any questions so far up to this step? All right. Well, now this is just a matter of, you know, first we have to get the antiderivative, which isn't hard. How many of you feel you understand antiderivatives a lot better now than when you first came into the class? How many of feel a lot like, wow, you know, I know a lot more about antiderivatives now? Okay, Nell, Eric, Esther, Michael, wow. Okay, Adriana, quite a few of you. So this is really just computing the limit. We're just computing the limit here. Well, we're going to compute the limit. I have to write out my antiderivative first. So I'm not saying a whole lot about these steps because I think they're pretty straightforward. But please ask questions if you have any questions. All right. Are we good? May I move to the next page? All right. All right. Next page. Okay. So we put in the values of that we put in our limits of 0 and t, put them in, or 0 and t squared, I should say. And now, you know, if t goes to negative infinity, what would t squared have to go to? Well, it would go to negative infinity squared, and that's just infinity. Okay. And so, but you have that negative there in the exponent in front of the t squared. So you really have here then e to the negative infinity. I'm talking about this part here. You have e to the negative infinity. And that's just 1 over e to the positive infinity. And that's why you get 0. And so that area is finite, and it equals -1/2. And if you graph that function, this is an odd function. This is an odd one. What I mean is, it is like f of x equals negative f of x. So well, and what I'm trying to say is, to the left of 0, x squared times e to the negative x squared, that graph is below the x-axis. And so the area would be negative. So therefore, we get a -1/2. And this means now we got to go after the second integral. Okay. This converged. But the integral, the area we're looking for, is the sum of I1 and I2. So now we got to work with the second integral, and we're optimistic that that integral should converge, because the integrand, the x times e to the negative x squared, is the same. So we're optimistic that that would converge. And so what we'll do is we'll just now compute that integral, and the process is the same. You're going to let u equal x squared. You're going to make that substitution. Okay, and all right, so let me give you a moment to copy that down. Okay, now let me see here. Colomb has a question. For the bottom of equation, shouldn't the integral be from 0 to t squared? Oh, good catch. Good catch. Thank you. Thank you. Thank you, Colomb. Let me fix that right now. This should be a t squared here. Absolutely. Thank you. Okay. Okay. And are we ready to move the next page? Is everybody comfortable? All right. Well, okay. And so I guess I have to fix that everywhere, right? So let me fix that. T squared, T squared, T squared, T squared. I'll fix it on my notes too. Coulomb gets a virtual candy bar. Forgetting that. When I taught, long time ago, I actually taught middle school for a little while. This is when I taught high school, a long time ago, or substituted, taught middle school for like 3 months. And this one fella, he used to clean my boards every day after class. And at the end of the week, I'd give him a nice, big candy bar at the end of the week. And he thought that was the greatest thing in the world, you know. Oh, did Tina comment on it? Oh, sorry, Tina. Thank you. Tina and Coulomb should get virtual. I have to give you a virtual candy bar. But yeah, he thought that was the greatest thing in the world, you know. But I wasn't cheap. I got him like one of the big chocolate bars, not like, you know, medium size. I got him a nice, like, dollar one, you know. So. Okay. So then the second integral is going to turn out to be a half. And so this means then that the integral is going to equal 3 times negative a half plus 3 times a half. And so the integral converges. So that was a lot of work, right? To get an answer of 0. But if you graph the graph on your calculator, you'll see that to the left of 0, the area is negative under this curve, and to the right of the 0, to the right of x equals 0, the area is positive. And because this is what we call in pre-calculus an odd function, it's symmetric about the origin. And so you have the negative area on the left and the positive area on the right cancel each other out perfectly. Now that won't always be the case, but what I mean is, you know, when we split integrals up, I mean that just happened with this one, but doesn't mean it has to happen. But because we had the odd function here, and you know, and we separated the integral at 0, it was fine. Okay, may I move to the next page? Are we good? I want to make sure I'm pacing myself good. All right. Well, then, since our integral from negative infinity to infinity of 3x times e to the negative x squared dx equals 0, the integral converges. 0 is a finite value. 0 is a finite value. Okay. Now the book has nice examples also, but I'm trying to add to the variety a little bit. All right, shall we move on to the next example? All right, very good. All right, here's the next one. Okay, I'll give you a moment to copy it down. Okay, so what's the issue with this integral? We look at of course, we look at the denominator. Well, okay, hold on. There's some interesting comments here. When x equals 0, 0 actually is okay, because 0 minus 1 to the third is equal to negative 1 to the third power. So it's not like negative 1 to the half power. It's not like the square root of negative 1, which, Rodrigo, would be imaginary. Negative 1 to the third power, when you put that on your calculator, what do you get? Negative 1 to the third power. You get negative 1. So because it's a third power, if you like graph y equals x to the third power, you'll see that function, the domain is from negative infinity to infinity. So 0 is okay. That's not a problem. And the other endpoint, 28, is also okay, because 28 minus 1 to the third power, that's defined. So the problem is not one of the endpoints. The problem is, as Justice pointed, as mentioned, is that x equals 1. At x equals 1, you know, when x equals 1, you're going to have, 1 minus 1 to the third, and that's where the discontinuity occurs. This function, 1 over x minus 1 to the third power is not defined at x equals 1. And x equals 1, that number falls between the limits of 0 and 28. So that's another example of an improper integral. If the function's not defined between the limits, it has an asymptote at x equals 1. Well, 1 is between x equals 0 and x equals 28. That also makes the integral improper. You cannot treat this like a proper integral and put in 0 and 28 and do it like a proper integral. Even if you magically get the right answer, you can't do it that way. So what you have to do is you have to split the integral up. You have to split it up at the x equals 1. You can't split it up at any value. but you're going to split it up at x equals 1. So this is similar to what you did in the last problem, where you split the integral up at x equals 0. Here you're splitting the integral up at x equals 1, because the function is undefined at x equals 1. So there's an asymptote there. And this is going to give you then two improper integrals to compute. Okay, take a moment to copy. Okay, so now we're going to evaluate the first improper integral. And incidentally, that is an integral of what type? Is I sub 1 type 1 improper integral or a type 2 improper integral? Type 2, that's right. That's right, Tina. And you know, here we are. So what are we going to do to integrate this? To integrate this integral here. Of course, we write the improper integral as the limit as t approaches 1 from the left. Now, why is that? Well, remember, okay, we're going from 0 to 28. The integral goes from 0 to 28, but we're breaking up the integral at x equals 1. And so the first integral goes from 0 to 1. So if we replace the 1 with the t, and we take the limit as t approaches 1 from the left, because that's what our limit is. We're approaching 1 from the left. And incidentally, the other integral, I2, would be the limit as we approach 1 from the right. But what would you use to integrate this integral? What procedure? Integration by parts, substitution, partial fractions. What's the right choice? Substitution. Always first think about the easiest choice, and then, you know, sometimes that may not work. Okay, so we're going to let u equals x minus 1, and when we do that, of course, our x limits of 0 and t become our new u limits of t minus 1 and negative 1. And then this is just standard integration. Okay, so write 1 over u to the third is u to the negative 1/3. And then the antiderivative of u to the negative 1/3 is 3/2 times u to the 2/3. How many can kind of do that in their minds now? Like a Well, I mean, I guess you'd have to, right? You'd have to be able to, right? But how many are finding it more instinctual, doing an antiderivative like that, than, you know, when you first came to the class? I hope it's all of you. Okay. Well, are there any questions up to this stage right here? Or up to this step, I should say. The integral now equals the limit as t approaches 1 from the left of 3/2 times u to the 2/3. Limits go from t minus 1 to negative 1. And all we have to do is compute the limit. So I'll move to the next page then, if we're good. Well, now we're going to put in our t minus 1 and negative 1. The 3/2, I factored that out, by the way. I factored the 3/2 out in front of the limit. And you will get negative 3/2 as your answer. All right, so this converged. No. Negative 1 to the 2/3 is equal to negative 1. Because negative 1 to the 2/3 is like negative, I'm sorry, that's a positive 1. That's like negative 1 to the 3rd, cube root of negative 1 raised to the 2nd power. So that equals negative 1 squared, which is equal to 1. And that's how you get the 1 here. Tyreek, are you good with that? I mean, is this, okay, excellent. Are there any other good questions? Okay, so we have convergence. And so this means we then will move on and do the second integral. Now remember, if this first integral, you're going to have problems where you'll do an integral, you know, you'll split an integral up into integral 1 and 2, and integral 1 will diverge. Well, if that happens, then the answer is divergence. Yes, not no. Question. Shouldn't the negative 1 be negative 2? Let me see here. I'm not sure. Are you able to show me with a mouse or like a drawing tool where your where you're talking about not Nell, what part? For the first one, remember what you're doing. You're going to put 1 minus 1. T approaches 1. 1 minus 1 to the 2/3 is 0 to the 2/3. Okay, which is 0. Okay.
But
Yes.
the thing is, we said we were using x as 0 and x as -1. That's why I understand you have to plug it in, but wouldn't it be -1 minus 1?
Let me see. Hold on here. Are we so you're all right. So what I'm trying to get, you're uncomfortable with one of the steps here in the big red circle, right?
Yes.
Is it the first line, second line, or third line?
The first one where I circled, you got -1. So like
Oh, you
previously,
circled that. Oh, okay.
yeah.
Well,
So
-1 to the 2/3. -1 to the 2/3. You can think of that as -1 to the third raised to the second power, right? Because you can multiply the exponents when you raise to a power.
yeah,
And so -1 to the third is -1, and we're squaring that, and that gets us a +1.
yeah. Like I understand that. What I meant is like for like over here we did t minus 1, and we had to do the same thing over here, but the second x was supposed to be
No, because that's just a number to the -1 to the 2/3. That isn't affected by t. That's a number.
because I thought we had to do 3/2 and then times x minus 1 and then plug in what x is for.
We did. Okay. But we did, going back to the previous page, we did, well, you mean what u is for. U was t minus 1. The limits for u were t minus 1 and -1.
Yes.
And we did plug those in right here in there.
Yeah, like that's what I did. Is just when I plug in, I understand one of the x's was -1, and we're subtracting a 1. So that's what I was saying. Shouldn't be -2 instead of -1.
No, because we're replacing this u here with t minus 1 and then with -1.
Okay, I see. Okay.
All right. Very good. Well, so now we're going to do the second integral, where that goes from 1 to 28. And the approach is going to be the same. You're going to let u equals x minus 1, but now t approaches 1 from the right. Because, you know, I mean, originally it was right, 0 to 28. And this 1 here now, for the second integral, we're approaching 1 from the right. And so the steps are pretty clear. Give you a moment to copy. Okay, and so the antiderivative of u to the negative 1/3 is the same as it was before, 3/2 times u to the 2/3. And now we substitute in 27 and t minus 1 for u. And you notice I'm carrying the limit all the way. The limit as t approaches 1 from the right. And what we're going to get here is we are going to get 27/2 is the answer. 27/2. And you notice that I don't drop the limit until I actually take the limit, right? I don't drop the limit till I actually take the limit. So if we put, as t approaches 1, this second term here, and incidentally, it's 2/3 power, not 3/2 power, 2/3 power. This second term is going to approach, this is going to approach 0 to the 2/3. Now I'm just, writing it down just so you can sort of intuitively see it, but this isn't like formal work what I'm doing, but I'm just marking things so that you can, understand the ideas. And the answer is going to be 27/2. I wrote it a little more nicely there. And so that also converges. Put that in blue. That also converges okay. Are there any questions? And I know it's a little, well, this is 2/3. You all see it. It's 2/3. Two-thirds here, 2/3 here. Yep. So what's our integral going to be then? What do we have to do with the 27/2 that we got from this second integral and the negative 3/2 that we got from the first integral to get the answer? What do we have to do? Add them together. And that's what we do. So we have a convergent integral, and that's the area. So you have to do these problems, like this kind of problem, when the discontinuity falls between your limits in the integral. You have to then split the integral up into two parts. It is possible, these kind of problems, to get the right answer and do it the wrong way. But I don't want that to happen, like on your next exam, for instance, because then you wouldn't get any credit for that, right? You have to, it would be like very wrong to do that. You have to split the integral up into two integrals in this kind of situation. Okay. Okay. Well, so Esther asked, would I give any example where the integral diverges? Yeah, I can give you an example. Sure. Sure, I can do that. Are there any questions? I want to give you a little time to work here, but yeah, I can do another one. Let's do another one. All right. Hold on here. Bring this up. There's a problem here. What I'll do, this problem, I'd like to get to this next example, but I'll put this on the recording. I don't want you to copy it down, but there's a problem you're going to have in the homework that deals with something like this. Okay? And what you have to do for this integral, this improper integral, is you have to recognize that e to the 2x is equal to e to the x squared. And it's going to be in the recording, okay? Because I want to give you a little time to work. All right? And when you do that, when you recognize that, then okay, what's going to happen is you're going to let u equal e to the x. You're going to let u equal e to the x. Okay. And then your integral is going to become a new integral with respect to u. But you might notice that, and again, you're going to have to look at the recording for this, okay? You're going to have to, pause the recording, copy it down. But you might recognize this as a one where you have to use your antiderivative formula that you learn in section 5.7. Okay, that would be this formula here. So when you do that, you'll apply the formula, okay, and you will be able to reach your answer. Okay, so I made it so that you can see all the work in the recording here, and then finally you'll get to you'll work it out and you'll get to the final answer. Okay, so that's how you work that problem. I was thinking of just showing you how to start the problem, but I think, and you could try to start the problem with that hint and work it out. But if you get stuck, it's there in the recording. Okay, let's move to one more here. Okay, give you a moment to copy this down. Okay, so look at this problem. Is there a, I mean, why is this improper, this integral? When x equals a fourth, that's right. So when x equals a fourth, that's right, Tina. When x equals a fourth, oh, you're right. When y equals a fourth, oh, yes. Right, when y equals a fourth, this is an integral with respect to y. there's a problem. At y equals a fourth, the denominator equals 0. So that and if 1/4, y equals 1/4, is between the limits of 0 and 1. So what are we going to have to do to this integral? What are we going to have to do? We're going to have to split it. That's right. Split it where? What value do we split it at? 1/4. That's right. So this is what we're going to do. We're going to split it at a fourth. And if you graph the function, well, you would graph 1/4x minus 1 on your calculator. But if you look at the function, you'll see there's an asymptote at a fourth. So you split it. Okay, so we have an integral 1 and an integral 2 to evaluate. So the integral 1 will, that's our integral from 0 to a fourth of 4y of 1/4y minus 1 dy. So we'll write that as the limit as t approaches a fourth from the left of 0 to t of 1/4y minus 1 dy. We replace the fourth with the t. So we're taking the limit, we're writing the improper integral as a limit of a proper integral. That's what you're doing. And of course, you know the substitution that you have to make is u equals 4 minus 1. And then under the substitution, your I1 integral will be the limit as t approaches fourth from the left of, that is a 1/4 there, by the way, 1/4 times 1/u du. And of course, the limits change. Now we have new u limits. Okay, we'll continue the problem, but so these problems, as you can tell, they take a little time to do. But that's how it is in math. You're learning more, you're getting more advanced, and so you're able to do a wider variety of problems. Improper integrals do have applications in physics and engineering, for instance. Okay, if you wanted to compute the mean life of an atom, you would need to use an improper integral for that, and you'll have a problem like that on your second batch of 5.10 exercises. Okay, may I move to the next page? Are we good? Are there any questions? All right. Do we have maybe a second thumbs up? I like seeing Tina's thumbs up, but let's. All right, Cologne likes it. He's good. All right. So, what are we going to do with this 1/4? By the way, this 1/4. What should we do with the 1/4? Take it out. That's good, Sir Fiel. That's right. Factor it out. Factor it out of the limit. You learn from your limit laws, you can factor out numbers. Okay, and so we'll do that. And so there's the 1/4 right in front. Getting pretty good with this mouse. I think I'm getting better. Now the antiderivative of 1 over u is the log of the absolute value of u. So of course, then we have to put in our limits of 4t minus 1 and -1. We have to put it in and as t approaches a fourth, now in this problem, I mean, are we good up to this step here? I want to make sure you're good up to there before I finish here. All right, so we have the log of 4t minus 1. As t approaches a fourth, what is 4t, or the log of the absolute value of 4t minus 1? As t approaches a fourth, what does this approach? As t approaches a fourth, what does 4t minus 1 approach as t approaches a fourth from the left? Not meant to be tricky. 4 times t minus 1 approaches what number as t approaches a fourth? So take 4 times a fourth and subtract 1. You get 0. Okay. Tyreek, you were close, and I thank you for your answer. I like answers, all answers. Okay. 4t minus 1 approaches 0 as t approaches a fourth. But you notice I don't put a fourth in for t because, well, what is the log of 0? -infinity. So therefore, this is an example of where we have divergence. Esther was asking to see an example of a divergent integral. And this is an example. Anytime the limit doesn't exist, or the limit equals, in this case, our limit equals -infinity. But anytime the limit equals -infinity, well, Tyreek, we can't plug in the 1/4 because we're doing it in our mind. If I plug in the 1/4, I'd have this. Good question, very good. If I plugged in the 1/4, I'd have the log of 0, right? If I put in 1/4, in other words, let me write it here. If I put in 1/4, log of 4 times a fourth minus 1. I don't want to get the math gods angry at me, but that's going to be the log of 0. Is the log of 0 allowed? No. So we can't do that. But as t approaches a fourth, we know the log of 4t minus 1 approaches -infinity. And that's how you do it. And so this is an example of a divergent limit. And so for this problem, we don't even bother now for the second for the I2 integral. We don't even bother. So thus, therefore, this integral diverges. The I sub 1 diverges, and hence the entire integral diverges. And that's how you do it. So you have some very good examples here to help you with section 5.10. The problems take a while, which is why I broke up the 5.10 exercises into an assignment that's due Sunday and another that's due Tuesday. It will take a while to work these. Oh, hold on. If it's approaching from the left, let me see here. One moment. Cologne's asking, yeah, you make a good point. You make a good point. What Cologne's saying is, if t approaches a fourth from the left, you wouldn't even, let's see, one moment. Hey. Well, I didn't even think about that. Cologne's saying we cannot approach 1/4 from the left, because if we were, it would be, well, no, we can, because remember, we're taking the absolute value. Remember, we're taking the absolute value. Don't forget that. Excellent question, Cologne. And so, even though it'd be negative, it would be back to positive. And so, okay, very good, excellent questions.